Hello friends. Today I am here to discuss about the topic magnetic effects of electric current in the way I actually understood. So, what does the magnetic effect of electric current term mean? It means that an electric current flowing in a wire also produces a magnetic field around it. Now, now let us learn about this topic in detail. This is going to be the first part of the topic. Now, magnets. We all know we had fun with magnets. Magnets are really fun. We used to play with magnets all the time. So, we all know what is a magnet, right? A magnet is an object that attracts pieces of iron, cobalt, nickel, and steel. So, we all know that a magnet is something that attracts iron pieces, steel, nickel, cobalt. So, what are these iron, cobalt, steel, and nickel called as? They are called as the ferromagnetic materials. Ferromagnetic materials. So, a magnet is an object that attracts ferromagnetic materials, other ferromagnetic materials. So, we have many types of magnets, right? We have the U-shaped magnet, bar-shaped magnet, etc. So, mainly we will be discussing about the magnet that is the bar magnet in this chapter. You all know what is a bar magnet, isn't it? You can see here I am showing you a bar magnet. A bar magnet. This bar magnet has some properties. It states that one of the properties that bar magnet has two poles, south pole and north pole. Right? Check here. It has two poles. One is the south pole and the other is the north pole. It has two poles. The second thing, which is a well known property, that is like poles repel and like poles attract each other. Now check. These two are the like poles. Like poles, we all know what are like poles. Like poles are the similar or the same poles. Now in this magnet, I am talking about the south and here also south. See what is happening? Are south and south attracting? There's no attraction between south and south. No. Now north and north, there's no attraction. Now unlike poles, one south and one north, they are attracting. One south and one north, they are attracting. Now one north and one south, they are attracting each other. See, they are attracting each other. Here, they are attracting each other. In the same, if I put these two, what is happening? See, there is no point of attraction only. See. There's no point of attraction here. Yes, there's a point of attraction. So these are the properties of magnets. Now getting into the other side. Magnetic field. This magnet that we spoke about is having its own magnetic field. What is a magnetic field? See that? The space surrounding the magnet in which magnetic force is exerted is called as a magnetic field. This is the magnet. The space around this magnet in which magnetic force is exerted is called as a magnetic field. Now, how much space comes under the magnetic field? See, I am taking a magnet here. How much space can I expect that this magnet is having a magnetic field? So the answer is clear. It's in the definition itself. The space surrounding the magnet in which magnetic force is exerted, the area only in which the magnetic force is exerted. What does the magnetic force exerted mean? That is the area which is responsible for attraction and repulsion is only called as a magnetic field. The space in which the attraction and repulsion is happening, that is also called that is only called as a magnetic field. Now, a second thing, another property, that magnetic field is a vector quantity. We already learned about vector and scalar quantities in our ninth grade, right? Vector quantity is something that has both magnitude as well as directions. In the same way, this magnetic field also has its this magnetic field also has both magnitude as well as the direction. Now, how can we represent this magnetic field? Is there something which helps us represent the magnetic field or indicate what helps us in indicating this magnetic field? It is something that helps us in indicating or representing the magnetic field, that is the magnetic field lines. Magnetic field lines. A magnetic field is described by drawing the magnetic field lines. How do we describe the magnetic field is what I told you. That is that they are described by drawing the magnetic field lines. A second. These lines are drawn to represent the direction of the magnetic field. They are not only used to represent or to describe the magnetic field, they are also used or helped in representing or indicating the direction of the magnetic field. What is the direction of the magnetic field? All this. Now, second thing. So, this magnetic field can be detected by using a bar magnet with the help of iron filings as well as a compass. Now let us see the methods in which we can detect the magnetic field. Now first method. To plot the magnetic field pattern due to a bar magnet by using iron filings. We all know how to obtain iron filings, right? Iron filings are obtained when you take the bar magnet and place it in the sand. You can obtain iron filings. Now, what are you going to do is that take a sheet or a paper or something, place a bar magnet in it. Place a bar magnet on it. North Pole and South Pole. Now, what you do is that sprinkle some iron filings. Okay, oh my God. Sprinkle some iron filings. And then, once if you tap on the board for several times, what happens is that this iron filings start arranging like this in this pattern. You can see in this way, the red dotted lines like this. You can see, right, how are they getting arranged. So this iron filings show the shape of the magnetic field produced by a bar magnet by aligning themselves with the magnetic field lines. So these are the dotted lines, are these iron filings. They're getting arranged with the help of or with the magnetic field lines. They are getting arranged. That is due to the magnetic field lines. These are the magnetic field lines. Now, second thing, to plot the magnetic field pattern due to a bar magnet by using a compass. Here, we all saw this is using iron filings, now using a bar magnet. How are we actually going to do this? That the same way you are supposed to take a drawing sheet, place a bar magnet. Now, here at this point, place a compass. If you place the compass here, it shows the deflection towards this point. Mark the point. If you place it here, it shows the deflection here. If you place it here, 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 here. At certain point, the deflection turns. See, it is turned. The deflection is here, 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 here. It is getting toward the downward direction. So based on these two experiments, I actually made a short video that I'll be uploading. So here I am placing a bar magnet. I mean the compass is showing the deflection here, here, then here, here, then here. Here, towards some extent, it is going this side, right? Now, join all these points. Here, here also we are already seen. Now, what you're supposed to do is that join all these points. You have seen in the previous also we can notice the things in the same way. Here, whatever you are able to see. In the same way, using the compass also, we can observe that there are something like this. What are this called? These are the magnetic field lines obtained by joining the various positions of the compass. Okay, this is how we are plotting the magnetic field. Now, this magnetic field also has its own properties. Now, let us check out what are these the properties of magnetic field lines. These are the properties of the magnetic field lines. The magnetic field lines originate from North Pole and end at the South Pole. They originate from the North Pole and end at the South Pole. What does this mean? Now again I am drawing a bar magnet. The magnetic field lines originate from North Pole means that they do start from the north and end at the South Pole. Here also they start from the north and end at the south. Main. Now this is happening outside the bar magnet. But do you know that this magnetic field lines exist inside the magnet also? I have recently got to know that. So what you are supposed to do is a small experiment again. Take a bar magnet and break it into half, like not half exactly. You're supposed to break it into the finest part, that is the smallest part. Now I am breaking it here, this much, okay? Still, it's having its own north and south poles. Still, it is having its magnetic field and then magnetic field lines also. So the smallest part which we are obtaining is from the biggest bar magnet only. From the big bar magnet only, we are obtaining the small piece of the bar magnet. It states that there is a magnetic field inside the bar magnet also, inside the magnet also. The direction of this magnetic field lines inside the bar magnet is from south pole to north. Okay, here we can see it is from north to south, but inside it, when it comes to the inside, it is from south to north. Now check. So what happens is that from here they don't stop. They originate from north, but they don't stop at the south. They again go back to north in this way. South, they again go back to north in this way. They go and go to. Why do they go? They form the circular loops. Okay, till they form circular loops, there will be the magnetic field lines do exist. Now, magnetic field lines are closed curves. Now, this is the inside path, inside whatever we are checking the magnetic field lines is actually an exceptional case, right? So, if you only check out the outer part, the outer part, if you're only checking the outer part, it seems that they are closed curves. They're closed, they're nowhere open. Open figure, closed figure, right? It is closed, it is nowhere open. So these magnetic field lines are closed curves. Now other property. The strength of magnetic field is indicated by the degree of closeness of the magnetic field. That is how close the magnetic field lines are. We can tell that the strength of the magnetic field is that strong. That is, where the field lines are closest together, the magnetic field lines is that stronger. This is so simple. So if the magnetic field lines are close, then they are having great strength, like very great strength. How close they are, how close, the degree of closeness determines the strength of the magnetic field. Okay, now second thing, let's have a start mark to this. The magnetic field lines do not intersect each other. Now, imagine that before going into this, imagine that these magnetic field lines are intersecting each other. One is A and the other is B. Magnetic field line A and magnetic field line B are intersecting each other at a point. Now, the magnetic field lines do not intersect one another. This is due to the fact that the force on the north pole at a point can only be one direction, right? That when the force on the north pole at any point, at the north pole at any point is only in one direction. But if these two are intersecting or crossing each other, the north pole at the point of intersection must show two directions at a time. The magnetic compass, if you place a compass, it should show two directions at a time, which is actually impossible, which is not possible for which is not possible to show two directions at once. So hence we can conclude that the magnetic field lines do not intersect each other. Okay. So this is the first part of this chapter. So hope you all got some clarity on this. Thank you.